I know you're hurt for time, so.
Yeah, let's not.
Okay. Do it next time, because it'll be a lot easier.
Okay. So, welcome back to another week in the Mad Scientist Laboratory. We've got some interesting things going on here, developing in a number of directions. We got the elevator in, and it's working. And so I rode up and down until I got seasick. Enjoyed that.
It even managed to take me up.
Yeah. That I'll give the on-prem folks a chance to go out and look at it before we're done tonight. So one of the things that we're doing here is we're going to have a presentation on radiation testing tonight, and we have assembled a new device, which we'll go into more, and we've got some more equipment on order that'll be here by next Saturday that dwarfs this one in terms of capability. So some really neat things, and we'll cover that. So first off, we're going to have a unit from Intelligent Design that's just been released to us not even 48 hours ago. So we're going to go ahead and have that, and then we'll come back in with a unit on radiation, calibration, penetration, and probes and so on.
Have you ever seen something or heard something that just didn't add up? Like you weren't getting the whole story? Modern science delivers amazing knowledge about the natural world, but some of the things we've come to accept as true are actually disputed by a number of scientists from around the globe. Depending upon each person's paradigm, people can look at the exact same thing and walk away with entirely different pictures.
Let's roll!
My name is Cutter Calloway. But I've been fascinated by the great questions of life for as long as I can recall. Where did we come from? Why is there something rather than nothing? I know I'm not alone here, so I want to take you on a journey through the elegant, beautiful, sophisticated creation we call home. This is the Paradigm Project. In this episode, we find ourselves in Newport Beach at a gathering of some of the world's most dangerous minds, a group of PhDs that dare to question neo-Darwinian thinking. For those of you who aren't familiar with Charles Darwin's theory that all of life evolved from random, undirected processes, hang tight and we'll unpack it for you shortly.
From time to time, we'll be using a number of film techniques that are often used to play tricks on the viewer's eyes. But don't worry, when it comes to science and scripture, there won't be any illusions, optical or otherwise.
Let's go meet our first expert. Speaking of which,
I should probably make myself look a little more presentable. That's better.
These rebellious, free-thinking scientists are part of a growing global movement called Intelligent Design. They're hosting a special event here in Southern California to celebrate the first meeting many of them had in secret 25 years ago to discuss all of their heretical ideas.
Cutter.
Hey there.
Nice to meet you at last. Yeah, that's great.
Dr. Stephen Meyer is one of the chief architects of the modern intelligent design movement. He's a former geophysicist and college professor and author of the New York Times bestseller, Darwin's Doubt.
So maybe give me the ground level layperson. I've never heard of intelligent design before. What's the first thing that we need to know coming out the door?
Yeah, well, intelligent design is the idea that there are certain features of the universe and life that are best explained by a designing intelligence rather than an undirected or unguided process like natural selection. The movement has gone worldwide, and the research effort has become much more mainstream as scientists within mainstream universities and research centers are approaching questions of biology and chemistry and biochemistry and biological origins from the standpoint of an intelligent design perspective. Whether we're looking at the very foundation of the universe and the fine-tuning of the laws and constants of physics, or whether we're looking at our planetary system, the way in which our solar system is fine-tuned to allow for life, that it seems to be fine-tuned to allow for us to make scientific discoveries about the solar system and beyond. And then when you get to the living realm, you have body plans and anatomical structures. Then when you go inside the cells, you find these little tiny nanomachines and this exquisite digital information stored in the DNA molecule. And every layer of the cell is revealing new and extraordinary complexity that we had no idea about even 30, 40 years ago.
With the discovery of DNA and the genetic information it carries, an entirely new layer of reality was revealed, forcing scientists to rethink the current paradigms.
In recent decades, science has revealed an amazing microscopic universe residing in each of us. Since DNA is literally at the core of the matter, let's go back a few years and take a closer look.
In 1859, Charles Darwin published a book claiming that all the different types of creatures on Earth came from a common ancestor, a really long time ago. During his travels, he noticed some animals had slight variations that helped them survive better than others of their kind. He proposed that these traits were passed on to the offspring, and eventually, given enough time, entirely new species would be created. This became known as natural selection, or survival of the fittest.
Back in ye olden days, before these fancy supercomputers and electronic measuring devices and all these great scientific methods, the human cell was commonly thought to be a piece of jelly or protoplasm.
Biologist Thomas Huxley even reported seeing living protoplasm in mud from the ocean floor, and it was commonly thought that life was spontaneously created in nature. Mice could appear from piles of rags, frogs from mud, and flies could spontaneously generate on dead bodies. However, in 1862, French scientist Louis Pasteur disproved the theory of spontaneous generation and received an award for his work. Side note, Pasteur's legacy still lives on today. We continue to use his method of pasteurization to kill bacteria in food. So if life wasn't created spontaneously, how did the original ancestor get here in the first place? In the early 1950s, Stanley Miller and Harold Urey went searching for the answer. They conducted an experiment to simulate lightning hitting a mixture of gases meant to represent the early Earth's atmosphere. The result was the formation of several amino acids, the chemical building blocks of proteins. Miller and Urey thought they had recreated the first step in the origin of life. Later, however, geochemists concluded the mixture of gases used was not realistic. When the experiment was rerun with a realistic mixture of gases, it failed.
Before the complex inner workings of the cell had been discovered, you can see why people thought all you had to do was shoot some lightning into some gas and voila! It's alive!
It's one thing to hear it from a mad scientist, but biology textbooks continue to promote the Miller-Urey experiment today. Another problem with the origin of life is explaining how amino acids could form a living creature in the first place. Ever seen your tub of whey protein pop out an amoeba? In 1953, James Watson and Francis Crick shocked the world with their discovery of the double helix structure of DNA. and Crick announced that they had found the secret of life. The structure could explain how DNA replicates and also how it carries information needed by the cell. But this still doesn't explain the origin of the information. DNA is extremely complex, and all organisms on the planet have it. So, where did it come from in the first place? Fast forward to 2011. The ENCODE project succeeded in identifying many functional elements in the human genome. Turns out we have over 3 billion pairs of subunits in each DNA molecule, which contain information necessary to build our bodies. For such an immense amount of information to randomly appear on its own would be like letters appearing out of nothing and forming around 1 million pages of highly organized information. Could all of this have really been produced by unguided natural processes?
Digital information directing the construction of mechanical systems. That's what's going on inside life. And that raises a really huge question, which is, where did the information come from? And I call this the Information Enigma. And this is where intelligent design comes in, because what we know from our experience, from our uniform and repeated experience, whether we're looking at a hieroglyphic inscription or a paragraph in a book, information embedded in a radio signal, whenever we see information, especially in a digital or alphabetic form, and we trace it back to its source, we always come to a mind, not a material process. And we're arguing that in the case of the origin of life, there was a master programmer responsible for the information that makes life possible.
Bill Gates, the man who helped revolutionize the world by creating Microsoft, said, "DNA is like a computer program, but far, far more advanced than any software ever created." We have tons of experience writing digital code and using digital information. One thing we know mathematically is if you have random changes to the zeros and ones in functional software, you will degrade and eventually destroy the functionality of it long before you would end up with a new functional system. Studies in biology show this same analysis applies to DNA code as well. So it takes intelligence to create information. If we saw a drawing of DNA in the sand, would we ever think it occurred from random mindless causes like erosion and wind? Look at how difficult it's been for tech companies to try and create life in the lab. From AI to robots to other experiments, it's so complex that even with countless billions of dollars invested, we still don't fully know how the human mind works, and can't even create the amino acids needed for life using purely naturalistic processes.
I think it's really important right now to critique Darwinism on its own terms, on scientific terms. The theory is in a state of crisis. It has been for a while. It does a great job of explaining small-scale modifications, like finch beaks that get a little bigger, a little smaller in response to changing weather patterns in the Galapagos. But it does a really bad job of explaining the origin of birds and animals in the first place. Natural selection explains the survival, but not the arrival of the fittest. Mutation and selection can't even explain the origin of a single protein. The general consensus in the field, even people like Richard Dawkins, who's a great proponent of Darwinian materialism, has acknowledged publicly that no one knows how the first life arose via an evolutionary process or a materialistic process.
Darwin's theory has evolved over the years into the modern neo-Darwinian theory, which assumes the first creature was probably a single-celled organism that formed itself, probably in the ocean. Somehow, this creature would have sustained itself long enough to eventually reproduce. As generations of offspring were created, beneficial mutations in their DNA would eventually create more complex features such as arms, brains, wings, and eyes, and eventually all the species we have today. Darwinian thinking is used to explain everything from why we make the decisions we do, like which foods and mates we prefer, to why humans have a tendency to believe in God. But there are serious problems at the foundational level of the theory. Despite the confident hype in biology textbooks and news reports, doubts about Darwinian evolution are growing among scientists. Darwinian ideas are so entrenched in our culture that it will take time for things to change. But that change has begun to happen.
What are the implications for this conversation for everyday people in the pews or everyday person just living their life as a Christian in the world, why should they care about this conversation?
We have an epidemic in this culture of, first of all, suicide. We're at all-time high rates, especially suicide among young people. We have an opioid epidemic. I think a lot of what drives the angst in the culture is a sense that there isn't or can't be an ultimate meaning to life. And that is, I think, actually a very rational response to the prevailing philosophy of our elite culture, our knowledge culture coming out of the universities, the law schools, the courts, the idea that matter and motion are all that ultimately exists, that at the end of the day, there will be a heat death of the universe, and that when we die, we rot. Then the worry that there is no ultimate meaning to life, I think, is actually one that makes a lot of sense. And it's something that haunted me as a teenager. And so I think the rediscovery of evidence that's pointing to the reality of a personal intelligence behind life, behind the universe, raises the possibility of a more hopeful answer to the quest for meaning.
I'm really beginning to see the gravity of this discussion and its importance on the world. It's amazing to hear so much evidence of design in the building blocks of life. DNA is especially intriguing as it truly seems to defy neo-Darwinian thinking. Well, it's time to meet our next world-renowned expert, Jonathan Wells. Dr. Wells has 2 PhDs, is a medical laboratory supervisor, taught biology at California State University, and has published many books, including the infamous Icons of Evolution, which discusses the use of outdated and incorrect evidence of evolution in school textbooks.
Hey, Dr. Wells, I presume. Cutter Calloway, yeah?
Nice to meet you.
Good to meet you as well.
Heard a lot about you.
Thanks, me as well. You want to come back and have a conversation with us?
Let's do it.
Great, all right. I hear you were a lifeguard?
Yeah, not a beach lifeguard.
Oh, okay.
I was a lifeguard for many years. I taught lifeguards.
We found ourselves a nice little place here on the beachfront.
Good.
You know.
The Paradigm Project, Jonathan Wells, make one.
It'd be interesting to hear you talk about what's the most exciting evidence you're seeing that points in the direction of God.
Well, I'm an embryologist by training. I always thought that in embryology, we saw the most evidence for design. Then I met a bunch of colleagues from other disciplines, and they all thought that in their discipline, there was the most evidence. The evidence is all around us, I think. When I finished my undergraduate work, which was in the sciences, I was basically an atheist. I just assumed that Darwinism was true. The more I learn as a scientist, the more design I see. We know now, which Darwin didn't know, that cells are incredibly complex assemblies of molecular machines that move cargo along microtubules inside the cell, like trucks on a highway, and they're very specific about where they're going. Other molecular machines unwind the DNA so it can be transcribed into protein, RNA and protein. When you look at these details, which we can now do with modern technology, the appearance of design is just overwhelming. I mean, these things don't happen by chance. I first saw design in nature, and then I read the Bible. I actually read it from cover to cover like a novel. I see it, among other things, as a history of God's relationship with us. Design, for me, is based, however, on evidence, not on the Bible. In the classic tradition, of course, they are both revelations from God, the natural revelation and the scriptural revelation. And they combine to give us a fuller understanding. They don't contradict each other, and that's how I see it now.
It reminds me a bit of Psalm 19, the heavens declare the glory of God, and then later in the same psalm, the law of the Lord is perfect and right. So it's both, here's this natural wonder proclaiming God, and then also God's law given to us. One without the other is hard to really make coherent, I think, but they're sort of partners.
Since I saw design and changed my thinking, I have never doubted it.
Just so we're on the same page, let's discuss a few definitions.
The word adaptation, of course, precedes Darwin, and it just means the ability of an organism to change to fit its environment. What it tells me as a biologist is that organisms are incredibly well designed so that they have the ability to adapt to their environment, within limits, of course. Another side of the coin is the idea of mutation, mistakes in DNA copying. They do cause some disease. One thing we know for sure from the evidence is that mutations do not lead to new species, new organs, or new body plans. That is what Darwin's theory requires.
Our understanding of the world is framed by a very particular set of pictures. For most 21st century people, the Darwinian picture is the default way of framing things. But what if we used a different frame? Would we see anything new?
Evolutionary thinking, that is Darwinian thinking, gave us the notion of junk DNA. We know that only 2% of our DNA encodes proteins. And for a long time, many biologists thought the other 98% was junk because they thought that evolution was accidental and the junk just accumulated. But anyone coming from a design perspective would have thought, well, maybe there's function there. It turns out that there is in much of that. And the more we look, the more function we find. So Darwinian thinking actually was a science stopper for a long time. Design thinking would have freed it up and encouraged research into this so-called junk DNA.
This is some pretty mind-blowing stuff. So why aren't we hearing this side of the story on our favorite nature show?
We're hoping our next expert can shed some light on this question for us. Dr. Doug Axe is already back at work, so let's hit the road.
Are you Dr. Axe?
I am.
Cutter Calloway.
Cutter, good to meet you.
Great to meet you as well. Is this your building?
This is the science building. I don't own it, but I have a spot in it. I can show you around.
Doug is a molecular biologist and the director of Biologic Institute. His experiments examining the constraints on the evolution of protein systems included inserting large libraries of mutated DNA into the cell. He surprised both himself and his colleagues with the discovery of just how fragile DNA really is. His work has been featured in many scientific journals.
Dr. Axe, which, by the way, is an awesome name.
I kind of like it, yeah.
Thank you for sitting down and chatting with us. A few questions really about your research and the things you're finding in your specific domain of the sciences.
Was in a molecular genetics course at Caltech on the way to doing a PhD there, and was learning about the control systems that are activated at the subcellular level, at the molecular level, how genes get upregulated and downregulated, and just found the mechanism to be absolutely brilliant. And that's when a light bulb went on for me, and I thought, hey, this is engineering at the molecular level. And I also thought the story of how these things come about through a natural process like random mutation and natural selection, I found that very unconvincing. I thought it'd be very interesting to go into the lab and do the work that would show whether that can work or not.
Really interesting. So you came from an engineering background,
Yeah.
asking the question of how might an engineer design this, is
Yes.
what you're asking. And do you, as an engineer, would you have had the capacity to design what you found biologically in life?
No way. You could get all the engineers together. Life is remarkable. Proteins are these long chain molecules that get made from genes. So one gene carries the genetic instructions for stitching together amino acids that fold into a protein, and the proteins fold into complex three-dimensional structures that do the actual molecular work of life. Chemistry, they make molecular motors, they make scaffolds for the cells. So every cell has thousands of these different kinds of proteins doing different jobs within the cell. As a believer who bases his life on the truths of Scripture, everything that I do is touched by my understanding of what's true, and Scripture is the big thing that informs me about what's true. I'm also being informed by simply looking at the world around me. If God did create the universe, then when you're studying things, you're studying the handiwork of God. Likewise, you can go to Scripture and study what we call special revelation. It's the stuff that required words to convey, not just, the big physical picture that we live within. So these are two things that I think are both equally of God, and I'm fascinated by and interested in the study of both. What I want to do when I go into a lab is simply go and do science extremely well and humbly. Because if we approach science humbly, just as if we approach Scripture humbly, we'll acknowledge there are passages where I don't know what it means. Scientists should be able to say the same thing. Here's the data. I could give you my interpretation, but it's my opinion being added to the data. I don't know what some of this means.
So really you're advocating for humility with all the parties involved,
Right.
in that sense.
That's maybe part of why there's so much tension at this dialogue between the two sides. If both sides could say, some things are very clear, And let me show you, and you'll agree with me because they're so clear, and some things are not so clear.
How do you balance pushing science that challenges mainstream ideas without the sort of lay audience going like, we can't trust any of it. None of them agree, none of them know what's going on, and they just become more entrenched in their skepticism. What does that look like to balance those two sides?
Well, it's a very complicated thing, as you know, if you're looking into this. I think if we back up and go to, shortly after World War II came to a close, there was an era there in the 50s and the 60s, the moon landing.
That's one small step for man.
Where it seemed as though science couldn't do anything wrong. It was paving the way to our future. And at the same time, we have growing in our culture an extreme skepticism toward politicians, toward lawyers, toward big business. And I think there's a healthy degree to which we should be skeptical. For a long time, it seemed as though the scientific community was exempt from that. If you have a white lab coat on, then everyone's supposed to say, well, you're the scientist, you're the expert, you know. The reality is the people doing science are 100% human. They're as human as the people doing business or politics. They do have their selfish interests. There's fame and fortune to be had in the sciences. And in that mix, the truth gets maligned occasionally. But a big message is you don't have to be an expert to enter into this. You don't have to have a PhD to be confident that your intuition that we're here because we're intended to be here is correct. You can do that from common sense.
Our view of the world is increasingly being influenced by big data and algorithms. We may think we're encountering reality when we look on our favorite social media, but the truth is, our pictures of the world are being manipulated and dictated to us by multinational corporations and other moneyed interests. These corporate giants reap massive profits by steering us toward certain products, thoughts, experiences, and even political candidates. And if that's the case, with all that information that's out there, how do we know what to trust, much less whom to trust? When you read online that scientists say, how do you know if it's all scientists, 100 scientists, or no scientists at all? Well, for starters, we need to do a better job of following the information back to the source for ourselves. But beyond that, in this information age, we need to develop wisdom and discernment. In this age of information, you can't always trust everything you see. One of the greatest challenges we face as people of faith in the modern world is that we're losing our ability to see through the lens of the other. It's almost like we've lost this critical capacity to empathize with, much less love our neighbor as ourselves, especially neighbors who see the world differently than we do. And the time has come for a radical rethinking of this paradigm.
Think I could get away with showing that at school? I'd sure like to. It's well presented.
Okay, let's see. Can everyone hear me?
Yeah.
Okay, all right. So we're gonna do a section on radiation tonight, and this is kind of a prelude. I imagine if the equipment shows up next week, we'll do it this week and next week too. And radiation is one of those things that you really can't overdo too badly. There's just a lot of real important content in science around radiation, because radiation is a much bigger subject than most people think it is. You have this idea that radiation is actually all about nuclear reactors and and such, and it is, but radiation is also something we use to see our world every day. We have acoustic radio energies reaching us. We have vibrations of several different frequencies reaching us, and our sensory systems detect that as heat and light, and we interpret our world very much by the use of radiation. So we are engineered to respond to radiation and see our world through radiation, and there is spectral radiation both above and below our capacities. And so we've come to understand through our rationality that we can extend our radiation sensing capability and actually look out into radiation that is coming beyond our senses and see the universe in a much broader sense. Real quickly, we have a device here that I'm going to be going into more that is capable of showing us very minute bits of information. Can I have a volunteer? I'm going to have to... Evan, why don't you come on up here? And I'll hook you up here. Show you a real interesting challenge. Okay, so now here's the challenge. This is, I want you to come around here, and I want you to kind of hold that up towards the camera, but don't exceed the limit of the cable, because then it'll jerk it out of your hand. But you're going to show the meter face to the camera. And then yeah, perfect. So you can see there's the meter face, and that is radiation that we're detecting right now. And what we have here is, these are 2-inch blocks of lead. We have actually 6 of them. And then we have 2 end pieces, which are also of lead. And they're around a 3-inch scintillator, which is a form of radiation detecting device that looks at gamma radiation. And so I'm going to remove the top bricks, which are 26 pounds a piece. These things are really heavy. I accidentally set one down on my finger over the weekend and cried. It was not a good experience.
You didn't turn my air on.
Interrupt me, slap me, call me stupid. You okay? Okay. So now we've opened up the top part of this, and all of a sudden you'll notice the meter is pegged. And I'm going to actually back it down one click so that you can see. We'll go through this again. I'll put the shield back in place. And you can see that the needle goes almost all the way down to 0. And then when I take the bricks off, the needle rises up. So what that means is this very sensitive detector in here is detecting radiation. Where is that radiation coming from? I want you folks to use your brain. we've got lead underneath, lead on the sides, lead on top. We've taken the lead on top off, and we're seeing radiation. So where's the radiation coming from? What direction is the radiation coming from? If we took the bottom off, the radiation would be coming from down. If we take the top off, where's the radiation coming from? Up. Okay. What's up? Come on, you're high school seniors and such. Give me an answer. I can't hear you. Turn on your microphones. What is up? Anybody?
Do you mean like what direction is up, or what is up that could be causing the radiation?
Yeah. Is there anything up that's causing radiation?
The sun.
Louder?
The sun.
The sun is what kind of a radiation source? It's a great big fusion furnace. Is there more than one? The sky is covered with stars. We have radiation flooding into us from outer space. Stop and think for a second. We've got a device right here on the table that is detecting radiation from outer space. And you're watching it happen. Gee, now what could we do with something like that? There's all kinds of radiation that, and radio telescopes and all kinds of astronomical devices that are looking at various kinds of radiation and various frequencies, seeing things in space that we can't see optically. One of the kinds of radiation that we can see coming in from space is gamma and neutrino cosmic radiation, and there's a lot of it, a lot more than you might think. Directly above us and also right out around the periphery of our planet is something called the Van Allen belts. The Van Allen belts trap ionized particles and radioactive particles, and there is extensive radiation in the Van Allen belts, and as a matter of fact, it's a hazardous area for the astronauts to travel through. So, having devices that can detect radiation, very sensitive amounts of radiation, is a big part of being able to see very small amounts of radiation. Well, why do we have these lead bricks around? Think about it this way. Have you ever played or worked around with an amplifier? So you have a pair of headphones on, or maybe an earphone, and you have a microphone. And you turn up the volume, and you can hear all kinds of noise and humming and blowers and all kinds of stuff that normally you can't hear because it's below the level of your perception just for your regular ears. But you turn up the volume, and now you hear all this background noise. Well, it's the same way with these tools. We have something called background radiation. And that background radiation is actually a problem for the various sizes of detectors. So I have a radioactive source here on the end of this probe, and I'm going to have my meter man here hold a different meter. Okay, yeah. Okay, so should be seeing. Okay, so we can see that there's radiation here, and it's making our little probe go up and down. Now, what's interesting about this, as you can see, that there's different levels of radiation. But I'm just going to take this probe off for a second, and I'm going to switch to something called a scintillator. Now all of a sudden, no matter where I hold this thing, that needle is pegged. And I'm going to turn it down another notch. There it starts to go down. But if I swing it back over here, it pegs it on a higher scale. So what we learned from that is that different kinds of probes have different levels of sensitivity. We have to think about what we're trying to accomplish and what kind of probe would best be used in such a case. So use case determines the sensitivity and the size of the probe that we're going to use. If we're interested in measuring very, very small amounts of radiation, did you ever manage to breathe again, or are you still holding your breath? Oh, you are, good, that's, all right. I am done with you, so I'm going to send you back to your seat. Thank you very much for your assistance.
Does the UVC lamp that we have over there have any effect on it?
This lamp, no, because it's ultraviolet and it's in the visible light spectrum. And UVC is actually up into the higher electromagnetic spectrum, just outside the optical range. You keep going up in that spectrum and you're going to start getting into X-ray. And then after you go through X-ray, you're going to get into gamma ray. And after you get through gamma ray, then you get up into cosmic rays. So
you're moving to higher energy but shorter wavelength.
Correct. So we're gonna start by just nailing a few fundamental terms. I want to talk about radiation types first of all. We're going to talk about radiation types that have essentially no mass, and then radiation types that have mass. And so we find of the mass related types of radiation, we have the proton, the neutron, the electron. What do you build out of protons, neutrons, and electrons? Someone take a guess.
Atoms.
Atoms! The fundamental building block of the periodic table. Atoms. Yes, atoms are a fundamental part of our reality. Does anyone know where atoms come from? All the different atoms in the periodic table. Well, we now know that the universe had a beginning, and that beginning is commonly referred to as the Big Bang. It was a singularity in which there was a tremendous balance of entropy that suddenly released mass, energy, time, and space all simultaneously. And the universe unfolded and expanded outward, and that expansion process is still going on. Furthermore, that expansion process is accelerating, and that is a very interesting feature. And the balance of the gravity against the balance of the expansion force, we have a number of things that we can't account for mathematically just doing arithmetic. So we have posited the existence of, but nobody has actually proved the existence of, something called dark matter and dark energy. And these things are necessary to explain the behavior of the universe, because the math doesn't add up. When we start looking at galaxies that are swirling, the outermost stars should just fly away, get flung off into space. They don't. And that would indicate that there is gravity holding those pieces in place in a way that is not readily visible in the amount of mass that we can see and that we can measure with the radiation that we can detect. And so we posit the idea that there is something out there that we can't see and can't detect, but it is still producing the necessary gravity. Well, the galaxies formed, and we had stars forming, and those stars, those furnaces, started burning tremendous amounts of hydrogen, which is nothing more than loose protons, and that hydrogen burned down into helium and burned down into the lower elements, and it kept on burning down and combining and refusing and recombining into larger and larger atomic material until it got to iron. Iron doesn't fuse. When you get to iron, the star blows up in a supernova, and it blows all of those constituent elements outward where they can form planets and asteroids and all kinds of other matter. And so we're actually made of star stuff. This tremendous amount of material we see in our planet, called the periodic table, is uniquely valuable to intelligent life on Earth because it's being mixed, it's being churned. There's tectonic plates floating on top and a giant washing machine of magma inside the planet that's constantly keeping everything thoroughly mixed and circulating that material back to the surface in a form that readily combines with nature to become Earth, which is an ideal environment for plants and animals, etc. So, yeah, the biosphere. Okay, so radiation consists of the protons, neutrons, electrons. We call beta, we call electrons beta particles if they are released at near light speed from isotopes. But they are in fact electrons, and they have a mass of electrons. And we can create electron beams at the same energies that beta particles move at. So really it's the same stuff, but for the sake of explaining this whole process, yeah, think of beta as a form of radiation that comes from isotopes, and electrons, when they're in a free motion, are usually associated with an electron beam. And we have electron guns and electron beam technology that started out in cathode ray tubes and in a whole variety of other vacuum centric devices, and today is still being used in things like electron microscopes. So then we have something called the alpha particle. And the alpha particle is a fragment of decay from uranium, and it's actually nothing more than the nucleus from a helium atom. It consists of 2 protons and 2 neutrons. So it has an atomic count of 4 total. An alpha particle is nothing more than a helium nucleus with no electron. Now, ordinarily, because the atomic number for helium is 2, you're going to have 2 electrons circling your alpha particle, which is your helium nucleus, and then you have an atom of helium. So when we ionize that, we take away the electrons. Now we have just the nucleus. We have an alpha particle, and we can take that helium gas and we can ionize it, strip the electrons, and then focus it as a beam, accelerate it, and do as an ion beam, create ion experiments. Now, on the other side of the coin, we have particles or radiation that essentially has no mass. They're thought of as waves, but sometimes they behave as waves, sometimes they behave as particles. We get into this wonderful world of quantum. So gamma, X-ray, and photoneutrons, or photons, are all part of this realm. And they're very, very fast. Gamma's a little slower, but X-ray and photon both travel at the speed of light. So, when it comes to measurement, when we start thinking about the measurement of radiation, we're going to look at some different properties of radiation and decide how we're going to measure them. So there's the quantity of emission, which is just the number of particles that we can detect with our probes. So quantity is a factor. The energy at which those particles are traveling, commonly referred to as the speed, is another huge factor. The faster these particles are traveling, the more energy we say they have. Commonly, you'll say, well, here's a beta particle. It has 400 keV. So that's 400 kilovolts of kinetic energy. It's just traveling at a specific speed, and that speed, instead of being expressed in miles per hour, is expressed in kilovolts. Maybe it's expressed in megavolts. So we have gamma radiation, cobalt 60 and cobalt 57 that can exceed 1 MeV, or 1 million volts of kinetic energy. So There's the energy of the emission. We have to think about the source of the emission. So is it an isotope? Is it an ion beam? Is it from fission? Is it from fusion? Is it a decay? Knowing a bit about what kind of a source we're measuring will tell us what kind of probe or technology to approach the radiation with. Something else we need to know something about is the penetration of the particle. Now, I have a box here with a whole lot of different thicknesses of material that start with literally chunks of lead and go all the way up to thin sheets of aluminum foil. And these are all calibrated, and there's very specific codes and information assigned to them. And so when we take a radioactive source and we place it so we're actually watching it, and then we place something in between, we can see that the needle drops. And depending upon the thickness of the material, we can see that thicker material has a much greater impact on the stream of particles than thin material. Can anyone suggest to me what this process might be useful for? Okay. Well, as I mentioned earlier, these particles have different levels of speed or energy. So particles with more energy are going to travel farther, and they're going to penetrate through more layers of material than particles with less energy. So we can actually use a calibrated system like this to determine what kind of particles we're working with, and actually gauge the amount of energy they have by the number of layers of material that they can penetrate. So that's one way in which we can ascertain that, because you think about it, okay, I've got a counter and I'm countering particles. Does this counter tell me how much energy that particle had? A simple ion chamber will not. One like this, it's called a Geiger-Müller tube. One like this, these are pancake probes. They will not tell you how much energy a particle has. A more sophisticated device called a scintillator actually can, but it has to be connected up to some rather sophisticated electronics. If you connect the scintillator up to something like a Geiger counter, all it's going to do is measure the counts. It's not going to be able to show you an on-screen representation. We actually do have software and devices here in the lab that we connect our scintillator up to, and we can analyze the energies and do a Pareto of the various radiation types in a stream and form a footprint, if you will, of the energy that's coming out of a reactor or out of a particular isotope, and the characterization of that energy will tell us what kind of isotope that is. So if we have an unknown source, for instance, We know for a fact that cesium has a very specific amount of energy associated with its gamma radiation. And when we connect the scintillator up to a computer and we get a visual display, we can see on a graph, this thing will identify exactly what frequency, or what energy that radiation is, and we'll be able to identify that as cesium or strontium or cobalt or some other isotope, simply by the energy involved. So while in the early days this was an effective method, it's not used much today, but it does serve to illustrate the different types of particles that we have. Alpha, for instance, will travel actually only just a few inches. I have a alpha source here. This is one that came from Russia. This is called polonium, and polonium is a strictly an alpha source. And so when I hold it up here, I really don't see any radiation at all reaching the meter. If I conversely hold my gamma source over it, I can see the needle move right away. But if I hold the polonium source, I see nothing. And I hold it down closer, I see nothing. And I hold it down closer, and I see nothing. And I go right down on it, and then bang, within the last 1 inch before I get to the meter, it literally pegs all the way over, just hard, bang. And I'm gonna attempt to show you that so you can watch this right down here, and you can just watch that dial, and right when I just get really close, that's when the needle jumps, which means that the radiation isn't traveling very far from here at all. Well, the reason for that is because this is an alpha source, and those are helium nuclei. And those helium nuclei are big compared to other forms of radiation. And so they have to push through the air, and they can't push through very much air before they lose all their energy completely and come to a stop. So alpha radiation, however, has a lot of kinetic energy, in that because these particles are very big, they're ejected at very high energies. We're talking 2.3 or 3 MeV, million electron volts per second. That's the I think polonium releases alpha particle at about 2 to 3 MeV, and that amount of energy in one of those particles, when it hits a piece of beryllium, it will actually chip away neutrons off of the beryllium atoms and release them, creating neutron radiation. So if I have a chunk of beryllium and I put it on my alpha source, I now have a neutron source, and I can measure little bits of neutron radiation coming off by creating that combination. So that's an alpha source. The next step up is something called a beta source, and I have a whole bunch of these. These are little sealed discs that are color coded. Some of them are green, some of them are orange, some of them are blue. The green ones are beta source, and that is they're giving off electrons. Now I have one here. This is titanium 204, and it is a 1 microcurie source, but it has another piece of information on here, and this piece of information is really important. It's called the half-life. And anytime we start dealing with radioactive materials, isotopes in particular, you have to think about, okay, what is the half-life of that material? I have here a radioactive source, and it's 1 microcurie, and it has a half-life of 3.78 years. That means that 3.78 years after this sealed source was made, there was only half as much of the isotope present in that source as there was the day that it was made. And in another 3.78 years, there'll only be a quarter, and then an eighth, and then a 16th. And so down it goes every 3.78 years until there's nothing left. So I look at my dish here, and I have another green one right here. This is strontium 90, and I'm putting it on the Geiger counter, and it pegs it. See if I can get a reading on this. This is 0.1 microcurie. We're still pegged. I'm going up to times 100 now. And I've got a little over 100,000 counts per minute on 0.1 microcurie. It's got a half-life of 28.8 years. So that's a really long time. Got some more over here. Here is an isotope. This is a gamma isotope. It is manganese 54. Okay? And this, the half-life on this isotope is 312 days. This sealed source was made in December 2010. I'm putting it on the Geiger counter. I'm all the way down at the lowest setting, and I'm getting background radiation. That's it.
Is there a certain number of half-lives that's considered you really have nothing left, or you?
When you get down below a place where you can't even read it on your Geiger counter, for all practical purposes, there doesn't appear to be a reason to say that the source is still active. However, we can do the math, and we'll always have some amount of radiation left. That's what math does in a half-life like this. but you're going to be dealing with such an insignificant amount that you may be waiting days for it to eject a particle. And you won't see it against all the background noise that's constantly going on, so you won't know when it actually emits a piece of radiation. I've got a piece of polonium here that has a half-life of 138 days. Oh, but I hold it up and it bangs the meter right over. It says March 2011 on it. The half-life is 138 days. Oh, but I did forget to mention that I replaced the polonium with a piece of americium from a smoke detector. And americium has an entirely different half-life. It does prove to be a very energetic alpha source, and so we can use it for cloud chamber experiments and that kind of thing. So we're looking at penetration, we're looking at half-lives, we're looking at the source of the emission, looking at the energy of the emission, the quantity of the emission. Now here's something in addition to all of these that we have to think about when we're talking about radiation, and that's something called the absorbed dose. The absorbed dose is actually measured differently and in different units than the number of particles or the count, the quantity of radiation that we're measuring. So if I'm measuring becquerels, I'm measuring the number of counts or the number of particles that are being released. If I'm measuring millirem, I'm measuring the amount of absorbed dose that a human being would experience if exposed to that radiation for a certain amount of time. And that time is usually 1 hour. So millirem per hour is a very, very common standard. And we have to think about that because you say, oh my gosh, this has got 500 millirem. That's a very strong source. Yeah, if you stand there for an hour, if you're there for a minute or two, you're going to experience a whole lot less ionizing radiation. And so there's a couple of things about radiation that are very helpful to understand. And one of them is the law of the inverse square. And that is radiation, when you move away from it, distance is your best friend. So here's some different forms of measurement. We have the becquerel, we have the curie, we have the gray, we have the rad, we have the sievert, and we have the rem. Now the rem, sievert, rad, and gray are all about absorbed dose. And they can be translated among each other. But going from curie or becquerel to millirem is a much more tricky calculation. There has to be a computational process that takes place where you look at the absorbed dose. The numbers are not the same. You can't just stick in one number and get out another number. They're two totally different ways of looking at radiation. So very commonly today, for most scientific measurement, we use millirem. We think of radiation in terms of absorbed dose because in almost all cases, we're concerned about what happens when you experience that ionizing radiation. And we're dealing with the safety of the radiation. So that's the majority of it. We've got a variety of different isotopes here. I just wanted to mention a few of these. There's strontium, there's cesium, there's manganese, there's cobalt, polonium, titanium. Oh, and one which I really love, this is called unknown. And actually, this is a fun one. They give you this, and you get to calculate the different energies that it produces and figure out what it is. And so, part of an interesting object lesson. Okay, so we're going to go back to this idea of different jobs for different types of meters. I've got a let's see here. I have an Eberline, which is an older detector. You can all hear it. And so I'm allowing the microphone in my headpiece to pick up a little bit of that. And that is a simple ion tube. And I'm going to take this connector and put it on the scintillation. And you can hear the difference that a scintillation detector is detecting tens of thousands of emissions coming from that radioactive source, while this little ion chamber could only detect a few hundred per second. So this becomes useful when you start dealing with a certain quantity of radiation. You don't want to measure very small amounts of radiation with a very skimpy probe because you're never going to hear them. Conversely, you don't want to go after a very large amount of radiation with something like this. You're going to overwhelm it. You're going to flood it. And you're not going to be able to distinguish what it is you're measuring. So you kind of got to match the probe with the radiation that you're measuring. Now there is a online calculator that allows you to key in information about an isotope and the number of days since it was created, and it'll calculate the half-life and the dose for you. It's very helpful information. These are some different types of measurement devices. Some of these we've talked about already. The scintillator, This is the Geiger-Muller tube. We don't have an HE3 tube present here, but we do have one in the reactor. The HE3 tube is a tube for measuring neutrons exclusively. There's also something called a proton recoil probe, which is another type of neutron detector. There are MSND semiconductor neutron detectors. We built cloud chambers and operated them here. An ion chamber is a simple smoke detector, or radon detector is a form of particle detector. Most of us wear a film badge. Hello, there's my film badge over here. And my film badge has, number one, a piece of photographic film in it that is used to detect gamma and X-ray radiation, but it also has something else. It has a CR39 chip in it, and that CR39 chip is to detect neutrons. So another very helpful combination tool. We send them out and they analyze the whole spectrum of radiation that you can get exposed to and send us back a report for each individual user over the quarter. This is how much radiation you were exposed to. So we've looked at penetration testing, some measurement and interpretations. Something we haven't talked about is calibration. Now, this particular meter has a tag on it, and this green dated card. This is the way they come from Ludlam after you've had them calibrated. This particular one will not have to be calibrated again until April of 2022. It was calibrated in April of 2021, so nice fresh calibration on it. And it now becomes the gold standard for us. And so I can take this meter, which has what we call an established pedigree, and I can take this meter, which does not, and I can set them up using a known amount of radioactive material at a specific elevation above the probe. And I can measure the amount of radiation that's striking the probe, and then conversely measure the amount of radiation that's striking this probe. I can look at the two readings, and by creating a mathematical factor, I can now calibrate this second meter. So this is called a transfer calibration. Transfer calibrations should never be more than one generation. In other words, you do not use a meter to calibrate a meter to calibrate a meter to calibrate a meter, because that will lead to tremendous errors. These meters, even though they've been calibrated and you have a first generation pedigreed calibrated meter with a fresh calibration on it, the error rate on these is upwards of 10%. So yeah, it's not like a watch. And you have to remember that when you're measuring radiation, it's really tricky business. There are sources of radiation around us we don't realize. There's radiation in the ground. Radiation reflects off of things. It bounces off of things. I've got enough sources of radiation on the table here that I'm creating a very confusing environment. This is a piece of uranium-238. It's in mineral oil, so it won't rust. But this is an actual piece off of a weighed uranium, or depleted uranium is often used to create very heavy weights or wing weights on aircraft. And so these weights are, sometimes they get broken up into these little jars that are for mineral, excuse me, not mineral, element collections. And people have these collections where they try to get all of the elements on the periodic table. This particular one came from such a collection. We have here a little bit of something called Yellowcake. Yellowcake is you can see why they call it Yellowcake. This is a sealed glass tube of it. Was made by some students and is a precursor, one of the precursors to making reactor fuel. And it involves nitric acid and some uranium chemistry that's really quite interesting, but you have to have proper facilities for it. It was not done here, and it was not done by us. It was donated to us because the party went on to college.
And the parents didn't want to keep it.
Yeah, and the parents didn't want to keep it. So we've inherited a number of sources that way. Okay. So we've covered alpha, beta, gamma, X-ray. We have a couple of different machines that produce X-ray here. We have the fuser, which we can use hydrogen gas in, and when we do that, we can create a plasma that produces only X radiation externally. Internally, it's actually producing a proton beam, but that proton beam never exits the chamber. What does exit the chamber, and what we could use that for, is a high energy directed X-ray beam. And so by collimating or focusing that X-ray beam, do a number of X-ray experiments. We are licensed to do such research, so if there is a student who wants to go experiment in the realm of X-rays, we've got the fundamental technology to do it. Just a matter of deciding what the experiment would accomplish and doing a proper safety review, and then we could proceed. At this point, are there any questions, both on-site or off-site, regarding radiation? Is there anyone awake, on-site or off-site?
If I'd have known we were doing this, I'd have worn my t-shirt that says, large letters, you matter, and then smaller letters, unless you move at the speed of light squared, then you energy.
Any questions? Okay. Well, that's pretty much the introduction to radiation. If you're going to work around the reactor, we do have the capacity to do activations where we actually bombard something with neutrons and create isotopes. Those are fun to do and detect the outcomes. Most commonly, we irradiate silver and create an isotope that has a half-life of just a few seconds, but it's long enough for us to measure the gamma that comes off of it. And we've actually made a neutron detector that's driven by that process. There's latency involved in its operation because it has to convert the silver into an isotope, but it does so at a very predictable rate based on the amount of neutron energy. Therefore, we can calculate the amount of neutrons that the silver is being exposed to by the amount of gamma radiation the silver is producing. And then we can watch that over time. And although it's not an instantaneous process, there's latency in it, we can get a very clear picture of the neutron production. Providing it's stable, that's a good cheap way of measuring neutrons.
Could you talk about the bubble detectors?
I have not. We did very early on in our operation use bubble detectors. We bought them by the fistful. They're very expensive, several $100s a piece. They last for 3 or 4 months. They detect only neutrons, but they are very accurate. And so they gave us information about the initial stages of the reactor development that we wouldn't have otherwise had given the instrumentation we had at that time. This device here has a 3-inch scintillation crystal, sodium iodide. We have successfully acquired from eBay a 5-inch sodium iodide crystal. These are great big, and more importantly, it's been mated with a 5-inch PMT or photomultiplier tube. So it's a matched window, 5 inches in diameter across a 2-inch thick sodium iodide, 5 inches in diameter. That's huge, and it will give us a very, very sensitive radiation detector. And we've therefore ordered a whole bunch more lead. Our mail lady will love us dearly. She tries to ferry that stuff up to the door. You get it in 26-pound bricks, and these I wouldn't want to carry more than one at a time. So lots of opportunity to do some exploration here in possibly food sources. So milk and other organic foods. We constantly on guard to see that radiation that's being released from Chernobyl getting into the atmosphere or coming from other sources gets into the plants, and that gets into the animals, and it gets into our food. So technology like this gives us very accurate indications of how much radiation is actually reaching our food.
Could you talk about the Canadian students who came here? What they carried?
Remind me.
I can't remember what they carried, but there was definite concern crossing the border with what they had because they brought something to show you.
Probably wouldn't be good for me to talk about that particular adventure.
All right.
But we did have a couple of Canadians come down here who were doing fusion research in Canada, and we collaborated with them. We'll help the Canadians build a fusion reactor. We have one of the few continuous on fusion reactors that is in operation on the West Coast right now. Most of the other fusion experiments are period-based, and they run for just a fraction of a second, and then the data is analyzed after the fact. But there are some aspects of fusion you just cannot look at. There's some aspects of the behavior of plasma and plasma stability that you just can't look at unless you have a continuous fusion reactor.
And we've run ours for 8 hours, right?
Yep, we've actually, and we didn't shut it off because we had to. We could have kept on running it, but I wanted to go to bed and have a meal, and so yeah, we knocked it off after 8 hours. Okay, if there's no more questions, that pretty well concludes the presentation I had for tonight, and we'll wrap it up. And thank you for coming. And